Okay. Hello, everybody. My name is Scott. I'm here from the University of South Florida. This is Discrete Math. Sorry about the technical issues, but my new toy just arrived. So, look at it. Isn't it pretty? So, anyway, that's my new toy, and it just arrived. So, I was like, oh, time to unbox it. I got a nice microphone arm. It's very nice. You don't care, but so that's why I'm running late. The volume's too low. Okay, so is that better? It's a new toy. I mean, I haven't. Yes, sound is left ear only. How do I fix that? Um, hmm. Properties. Okay, so I don't know how to fix that yet. Yet, I should look it up. Okay, so I don't know how to fix the toy. We will do this. There we go. Now we should have audio in the regular place. It's not the nice crisp audio. Have you tried turning it off and turning it on again? Yes, I did. So we don't have the cool audio yet, but the cool audio is arrived. It looks beautiful. Anyway, so I spent the time that I was supposed to spend, then the computer wanted to restart when I installed the software for the whatchamacallit, nope, that's the microphone. My computer had to restart when I installed the Scarlett Solo thing, and it messed up all my windows. Yeah, it says fine now because I changed the microphones back to this thing, which is not the cool microphone. So I'll work on the cool microphone and we'll have it working for next time. But as I said, it just arrived, so I was like, oh, grab it. So, any questions before I get started? Okay. Yeah. So let's see. I've got two gains on this thing. I've got a button that says 48 volt. I've got another button that says air. What does that do? Anyone know what that does? Nope, still only one. So. Okay. So anyway, the cracking a cold one, it is approved. Diet Pepsi, no alcohol involved. Alcohol can happen if after class. None during class. And I'm towing that line. So anyway, I announced on the Gradescope, yes. So I put the assignment for uploading the notes in Gradescope, but then when I saw there were only 53 uploads, I realized that I didn't put the announcement on Canvas, the assignment on Canvas, so that it would show up in your little thing. So I set it up to accept submissions until tomorrow, even though the due date had passed. So you can submit your notes for last week until tomorrow evening. That'll work. Okay, well, let's go over this quiz I gave you here. So today's goal, I want to go over some of the test stuff because it's really important. And then today's goal is to kind of finish up this idea about deep induction being recursion and then go straight into recursion. So we'll play a few games. I'll point you to a game called the Tower of Hanoi, which kind of points to this. And your book talks about the Tower of Hanoi, and your book has a really nice presentation in it. And then there's some places that you can see it online. And then I fixed the code I actually wrote it in PHP. I fixed the code for the thing I was talking about last time, so we'll be able to talk about that. But let's talk about this quiz. Okay. So what I wanted to do was go over some of the things that were commonly missed on the test. And this question, what 15 choose 0? This thing is asking how many ways are there for me to give you 0 cards if I'm holding 15? Which is a weird question. So how many 0-sized subsets of a 15-size set are there? Okay. So if I have 15 elements, how many subsets have nothing in them? And it's not 0, it's 1. There's one subset of 0 size, that's the empty set, right? So if I have the letters, if I have A equals A, B, C, then A choose 1 equals the set containing the one element subsets of A. But remember that A choose 0 is the 0 element subsets of A. And how many are there? There's 1. There's one 0 element subset of A. And that's the empty set. So A choose 0 would be the set containing the empty set. Okay? So the answer to this is 1. There's one set there's one set in 15 choose 0. There's one set in the integers 15 set integers. There's only one subset of 0 size, right? And that's the empty set. How do we feel about that? 1 to 5. Oop. I forgot. I lost my. Sorry, I lost my my clipboard too when the thing restarted, right? Because I had 5 poll all set up for the clipboard. Okay. Okay. All right. Or it's the number of ways to deal 0 cards, etc. All right. Okay. Let's talk about this next one. This one was commonly missed. So most of you got. How do I get rid of the draw? Get rid of the ruler there. Okay. So on this next one, which one's the binomial theorem? Is this one? No, this is kind of, 0 choose 4. That doesn't make any sense. These don't make any sense. Okay, what about this one here? What's this expansion here? That's our typical binomial expansion. So that's one. Now, if I simplify these coefficients, I wind up with 4 choose 0 is 1. 4 choose 1 is 4. 4 choose 2 is 6. Oops, not that one. This one. So this one right here corresponds to that one. So most people got those two right. There's one more on there that's the same thing. Which one is it? It's this one. right there. Because this right here, 4k equals 0, right, is this thing equals, I'll start with 0, 4 choose 0, a to the 0, b to the 4th, plus 4 choose 1, a to the 1, b to the 3rd, plus 4 choose 2, a to the 2, b squared, plus 4 choose 3, a cubed, b to the 1st, plus 4 choose 4, a to the 4th, b to the 0. And that is the exact same thing as 1 Yes, I think the system does give you partial credit, but I'm not 100%, so it should be checked. So, I mean, you could check it on yours. So this would be 1 b, this is b to the 4th, plus 4 a times b cubed, plus 6 a squared b squared, plus 4 a cubed b to the 1st, plus 1 a to the 4th, and that is the exact same thing as that, just in reverse order. Okay, that one was hard. That one was tricky. How do we feel about that, 1 to 5? Okay. That one was tricky. Okay. Let's go to the next one. How do I do this one? What's the really fast way to do this one? So what would Fermat give me here? Okay. Fermat would give me the formula. So if I used Fermat, okay, I would know that 4 to the 4th is 1, right? So 4 to the 5 minus 1, which is 4 to the 4th, is 1. All right. So that gives me, this thing here is 4 times what? So it's 427. That's hard, right? So 427. Oh, what would be 4 times 6 would be 24. That's a little bit nicer. So this is 4 to the 4th to the 6th times 4 cubed. Okay. So this is 4 to the 4th, which we know is 1, to the 6th. That takes 24 of them. And what have I got left? I've got 3 left. Right? This here equals 27. Okay. So this is 1 times 4 times 4, 16 times 4, times 16 times 4, which is the same thing as 1 times, okay, let's see, I'm doing mod 5, right? So that'd be, what is 4 times, what's 4 cubed? What's 4 squared? Mod 5. So this becomes 1 times 4, and that equals 4. Okay. How do we feel about that one, 1 to 5? So 1 to 5, how do we feel about that way? What I did was I used format. I knew that 4 to the 4th was 1. I actually know that 4 squared is 1, but by format I knew that 4 to the 4th was 1. So that got rid of all these. And then I had 16 times 4 left. Well, 16 times 4, 16 is 1. So all I had left is that 1 4 at the end. There's another way to do it. What's the other way to do it? Yes, 16 is 1 mod 5, because I'm dealing in mod 5. 4 times 3, yep, I could have done that. There's an even better way to do it. Okay, and I mentioned this on one of the quizzes. 4 to the 27th, 4 equals -1 in Z5. So 4 to the 27th equals -1 to the 27th. And 27 is odd. And there's the really slick way to do it. Okay. How do we feel about that 1 to 5? Because I'm in mod 5. I'm in mod 5. That means 4 and -1 are the same thing. Instead of going forward, I went backwards. Right? Instead of counting 4 forward, I counted 1 backwards. Right? That's -1. Well, -1 to the 27th. 27 is an odd power. So anything to an odd, -1 to any odd power is simply -1. And then, I got left with -1, and -1 is 4. It's kind of the slippery way to do it. Okay. All right, this one was missed a lot. And I was asking another instructor why, and he said that I was conducting psychological warfare, and this question was mean. If p and n are both integers, and p is greater than 2, and if p divides n, then n to the p minus 1 mod p equals 0. True or false? And the answer is that's true. Why? This right here, p divides n, means n mod p equals 0. So I don't care what that is. I don't care what the exponent is. N to the anything mod p is 0. Okay. How do we feel about that? 1 to 5. Okay. That one was hard. That one was hard. I got, I looked back, after looking back at it, I was like, yeah, that one was really hard. So, Okay. I don't like that one. Here, I'll tell you what. I'll give you an emote for that one too. Here, hold on. There you go. All right. This one right here, the prime numbers are countable. Is that true or false? That's true. How do I know the prime numbers are countable? There's an infinite number of them, but I can list them in order. Okay. Yes, so it's because the prime numbers are a subset of the integers, but it's more than that. They're not a finite. They're an infinite set of they're an infinite subset of the integers, right? It's not enough just to be finite. It needs to be, it's not just enough to be a subset of the integers. It needs to be an infinite subset of the integers, right? Because it's got to be big enough, right? So that's the idea. I can't order the real numbers, like this in a way to put a one-to-one correspondence with the integers on it, but I can do it with the prime numbers. Okay, and then name one thing you found memorable from the last lecture. Very cool. So 1 to 5, how do we feel about that last one? Okay. All right. Let's talk about new stuff. Class notes. So last time we were here. So last time we got to this point where we wanted to do, it's this one, right? Yes. So the last, there's a question about that last one. You should get 9 out of 11 because the last problem is actually worth 2 points. It is worth 2 points, right? What did I say it was worth on the thing? Oops. Okay. Wait. I don't know. This one should have been worth 0 in on the thing. Okay, there's the problem. 13, that's the problem. So it shouldn't be 13b. The last question should show 0 points. So I'll edit the thing. I'll make it show 0. That'll make it an out of 10. Now, why you got 9 on the 11, why you got 9, I don't understand. Unless I messed something else up, which is totally possible. I will go back and look at it. But did you click all these and you entered 1 in? All right, I will look at it again. I might have messed something else up on the quiz. But this problem right here should be worth 0 online, and it's probably worth 1 right now. And it could be worth 2 by accident. So I can fix that, but I can't do it right now. I'll do it after class. Okay. Yes, there's probably a mistake in the thing. So I'm going to move on now and not talk about that anymore. I will get to the bottom of that. Okay, so we ended last time, and we were kind of stuck right here because I didn't really have the algorithm completely worked out before I started talking about it. So what I did yesterday, among with all the other stuff, is I actually worked out what the algorithm should look like. And then I closed Ubuntu because my computer restarted. So just to refresh your memory, this is what we were doing. We had show for any positive integer n and any positive integer d, there exist non-negative integers q and r, so that blah, blah, blah. And what I had was this if n equals 1, that I had this idea. Suppose that if for all k from 1 to n minus 1, this thing, and then we did this induction. And the idea was to scoop down. But of course, I confused this bit here. This is all fine, but this part was confused because I didn't have the algorithm, the code completely worked out. So yesterday I worked out the code, and today I finished it. And so let's put the code up here. Let's get rid of all this. Let me see. Let's go here. Let's get rid of this. Let's get rid of this. This is boring. Now let's see the code. Okay. So last time I was kind of here and we were doing the proof by induction. So if I pull up the code, do you all remember this bit of code from the division algorithm code? So that's what we're doing here. So the algorithm that we had for the division algorithm, which is right here, was this. We had a while loop. I had a deck of cards, correct? And then I would subtract 3 cards off at a time. And then that's how I would get, right? So I had 52 cards or however many cards. And then say I was dividing by 3. I would take 1, 2, 3 cards, and then another 3 cards, and then another 3 cards. And eventually I'd wind up with a stack, and I'd count my number of piles. So every time I took off 3 cards, I would count it. Okay? So 1 to 5, how do we feel about that? The old division algorithm, right? Oops, dadgummit. Where all I would do would be, would subtract each time. And I did this over a loop. Okay? So I had this little while loop in here. All right. So what we're going to do now is we're going to make the exact same thing, but we're going to make a recursion. So instead of doing a loop, a while loop, I'm going to have the function call itself. Okay? So let me show you what this looks like here. Let's see, I got to go to Documents. This is Discrete. All right. So what I'm going to do is when I execute this code, it's going to go over and over and over again until I get to where I want it. Okay? So let's just review what that looked like. So when I execute that code, oops, one more, it looked like this. Okay? So the first loop, it got 27, then it subtracted. Here I'm running it on 32.5. So it subtracted 5, then it subtracted 5, then it subtracted 5, then it subtracted 5, then it subtracted 5. And I was left with 6 and 2. Okay? Yeah, let me figure out how to do that. I don't actually know how to zoom in this window. There we go. Hold down Control and hit the. Very nice. What you do is you hold down Control and you hit the and you advance the mouse button. All right. So if I do this again, so again, this was this code running, and the code that was running is this bit right here. Okay. Control plus didn't work. It was control scroll wheel. So anyway, I don't know why control plus didn't work. Maybe I had to hit shift. Or maybe I needed to use the numeric plus. I don't know. Anyway, so here, that was this while loop. Can remove D loops. Okay. Now what I'm going to do is I'm going to define this thing recursively. And a recursive definition means that what I wanted to do was I want it to go backwards. I want it to keep calling itself. Okay? So we had this idea that what I need to do is scoop down to get at what I want. So in the induction, right, what I was doing is suppose that if for all k from 1 to n minus 1, it worked. All right? And then what I want to do is I want to call these previous cases. And I'm going to do that here. So what I'm going to do, it has to accept an array as an input and give an array as an output. Okay? So that's the major change that had to be made. So what it's going to do is it's going to take this array with A, it's labeled something labeled A and the divisor labeled D. And then what it's going to do is it's going to have a counter. Now, if the array that I initialize with doesn't have a counter in it, it's going to start the counter at 0. Okay? It's going to initialize a new counter. So what's going to happen? Remember all these things. If, these are my base cases right here. If Q equals 1 and R equals 0, I'm going to return, I'm sorry, if A is 1 and D is 1, I'm going to return Q equals 1 and D equals R equals 0. Okay? That was that base case, right? Because that's what, because N equals 1 times D plus 0. And if D is greater than 1, then I'm going to return Q equals 0 and R equals 1. Because I'm going to have a remainder of 1, whatever the divisor is. Okay? So how do we feel about that, 1 to 5? That. Okay. And that's this case right here. If A equals 1 and D equals 1, so this line in the proof corresponds with this line of code. Likewise, this line in the proof corresponds with this line of code. Now, if N is less than D, in other words, if A is less than D, or D is greater than A, I'm not going to have any quotient. All I'm going to be left with is remainder. Okay? How do we feel about that? 1 to 5. If all I've got is, if I don't have, if I'm trying to take more cards from my stack of cards, I'm not going to make any piles. Okay? I'm just going to be left with the remainder pile. Okay. So I just return, I tell the thing that the remainder was A, was 1. I'm sorry, was A. Now, and then counter, because I didn't cause recursively, Q is going to be 0 if there were none initially. Now, if I don't get an answer, otherwise, anything else, what I'm going to do is I'm going to increment the counter. I'm going to say counter equals 1. I'm going to say A, my new A, equals A minus D cards. And my D is just D. Okay. So how do we feel 1 to 5 about what's about to happen with this recursion? How do we feel about what's going to happen with this recursion? Okay. So let's do it. And I've put debug code in here so it will output a trace to the console, which is what we want. So let's look at what this thing does. Whoa! What did it do? Well, the first time, well, for starters, the question is, will I be distributing notes on this, or do you have to be copying it down? The code, yes, you'll be able to get, but more to the point, the video is here too. So if you want the code, I'll be happy to post the code. Remind me to post the code, I'll post the code. So if my TA could remind me to post the code, I'll make sure I post the code. So what happened here was this. So this is the loop run, and it returned this array. Now, when I did it by recursion, 32 and 5 were my numbers from the initial again, right? I just put it in array form here. Now, the first time it ran through, it didn't have it had no counter. So it set the counter equal to 0. And then it called itself again. But this time it called itself with a counter of 1. And then it subtracted 5 from the 27. Okay? And then D, of course, it left as D. And then it did it again. It called itself again. And then 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 it called itself that one last time and reached this. That one last time, D was greater than A. Okay? And it broke out of the chain. It stopped doing the recursion and went, oh, okay, D equals A. I'm going to return Q as the counter. I'm going to return the counter as Q, and I'm going to return A as R. How do you feel about that? This process, this recursion. And recursion is hard, okay? This is one of those things that, they pounded the computer science people over and over and over again. Recursion is hard. So what I did here oops, I don't want that. Cancel. Let's see. No. Sorry, I'm trying to screen snip this into the notes so I can draw on it, and I'm failing horribly at this process. Okay. There we go. So when I did this, it's not just the basic definition of recursion. I'm really interested in the process. And more to the point, the thing I'm really interested in is the connection between the algorithm for recursion and induction. I'm interested in comparing these two things. This is what's really important, is this connection. That a proof by induction is really an algorithm of recursion. Because that's going to make this process. Any system of logic that I have capable of induction is recursive. Okay? And that's going to be extremely important to us. Okay? So the idea here is that any system of logic capable of recursion, capable of induction is recursive. And that's the key to Gödel's incompleteness theorem, is to understand this. What else it means is that anything that I can do with recursion, anything I can do with a while loop, I can do recursively. All right. And there are languages out there that, the computer languages that only do recursion. Okay. And this is something that's means something for us, because it means we can't check loops. And I'll show you what I mean by that in a moment. So this line here corresponds to that there. This corresponds to that. Those are my base cases. This is my concluding case. And this is my induction. No, this is not that. Okay. So how are we feeling about this 1 to 5? This is weird. This is hard. I'm not willing to. I'm not saying it's not. Okay. Okay. Now, let's do an example here. This is called the Towers of Hanoi. So if you ever get bored, there's a website called Math is Fun, and one of the problems on it is called the Tower of Hanoi. Has anyone ever played with this before? The objective of the game is to get everything here to everything there. So, let's see. I do that. Correct. I do something like this. I do something like this. I do something like this. Then I move this over here. I get that. I do that. And I do that. I did it in 9 moves, and the minimum number of moves is 7. So, any question about that? So this problem, this particular thing is called the Tower of Hanoi. And the point about the Tower of Hanoi is that it's recursive. Okay? That's the whole point of this game. So if I start with 3, right, I do this and I do this here, And it shows the minimum number of moves to get this done. And it's an algorithm, right? It does this thing first, and this thing, this thing, this thing, this thing. But if I have 3 toys, right? If I have 3 discs on the tower, what happens if I add another disc? If I add another disc, then my solution to the problem is to solve it for 3 and then run another algorithm on the 4th. The only difference is when I solved it for 3, I used the middle as the solution space. Oh, let's do it again. Here it is for 5. What am I going to do? I'm going to solve it for 3. Then I'm going to solve it for 4. And then I deal with the 5th block. Does everyone understand what's going on here? I've got an algorithm that's going to do this again and again and again and again and again. And it's going to do it by having an algorithm that runs recursively, okay? It solves it for a short stack, and then it's got, every time it wants to do it for something bigger, it just does it for, the short stack, and then the next one, and then, so on and so on and so forth. How do we feel about this idea that this is this is a recursive game? So 1 to 5, how do we feel about that? Oops. Okay, and my point of doing this, is because there's a very, very, very good description in your book about this and about recursion. And I was going to go over it all the way, but I spent too much time going over this other stuff, and I want to get through to the next bit. But if you turn on page... If you turn to page 328, it's chapter 5, it's example 5.6.5. And yet we'll talk about these recursively defined sequences and the fact that the sequence is defined is part of an algorithm. Okay, so it'll actually go through and talk about the sequence. Okay. And then you can find all of the sorts of code online about how to do it. Are there any questions about that? Questions? So there's the, I stole this from Wikipedia. I should say where it came from. There's the explanation. But notice here, I start treating each block as just a whole block. So I start with a game of 4. Here what I'm doing is I'm running the algorithm for a game of 3. I'm going to recurse. I'm going to go... I can't do anything about that because 3 is not 2. So I go back to the algorithm for 2. And now I run the algorithm on 2. I put that there, right? And then I put that there. And now I just treat this as a block. And then so on and so on and so forth. And there's a good explanation in that. So, yes, as I said before, if Michael will remind me, I'll put up the notes and everything. Okay. And then it's got a very nice talk about the recursive implementation. Okay, so if you go to that same Wikipedia page, here I'll just steal their code right now because it's got a nice little pseudocode implementation. So the thing calls itself again and again and again and again. Screen snip. So here's the recursive code that the thing's running. And again, I wanted to put this on here because not only is the book, not only does the book have good code, there's on the internet, you can find all sorts of pieces of this code. But notice here what's happening. It call the move is the function. And if you don't have it, it's going to call itself. And then it's going to call itself again. So it's recursive. How do we feel about that, 1 to 5? Oops, can't do that. Okay. Would you like to see another example then? All right. Let's do, I've still got a lot of 4s and 3s and stuff. So let's do another example. The Tower of Hanoi is something that you should play with at home. Let's do another example. Let's write a recursive function that calculates the factorial. So what I want to do is I want to write a function that computes this thing. Okay. Now I could do a loop, but it's not so much simpler, there's a clever way to do this. Okay. So I'm going to take an integer, n, it's a posint, n. So input. So by function, I'm going to name it fac. And it's going to take a posint n as its input. And then what I'm going to do is I'm going to say, okay, so I've got a function. I'm going to take it, and I'm going to say, okay, I'm going to take n. And if n equals 1, what am I going to return? What am I going to do? Right. Else, return n times fac n minus 1. Okay, so what's that going to do? How is this function going to work? If I give it 5, what's the function going to do? Okay, if I run fac5, what's it going to do? Okay. The function's going to do what? Return fac5 times fac4. And then it's going to do return. This part is going to do return 5. Sorry, not return 5. Return 4 times fac3. And then it's going to return 3 times fac2. And then it's going to return 2 times fac1. And that last one's going to return 1. So then it's going to do all of these things, and then it's going to count back up, right? Then the machine's going to do 1 times 2 times 3 times 4 times 5 as it goes back up the line. Okay? How do we feel about that, 1 to 5? Bugger. How do we feel about that? Okay. But look at what the machine's going to do here. The machine was already doing the exact same thing here. Here, the machine kept calling itself. So if I pull back up that code, here the machine was doing the exact same thing. It started at 32.5, and then it called itself. 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 Okay? So this idea of it just calling itself again and again and again and again and again. Okay? And that's the essence of recursion. Okay, are there any questions about this? This is deep. And I'm fine with the fact that we didn't get all the way that I wanted to get done today. We'll do the other one next time. The last example next time. Okay, so you got that example. The problem is that this example doesn't have a proof associated with it. Okay? And that's what's important. The reason why this right here, I mean, the proof, the factorial is well defined. Well, duh. Okay? I guess you could call that a proof. Okay? But the proof associated with this one has a proof associated with it. There's an inductive thing happening. Okay? There's some piece of induction and there's some piece of recursion, and that these things are connected. And that is actually the more important part for our purposes. Okay? this connection between the math and the code. Math, code. That an inductive argument is recursion. Okay. Okay, so we did this. I'm going to cheat you out of 5 minutes of your education. So today what we did, I didn't even do a thing. So today what we did was we finished up the recursion. So today we finished recursion. The Tower of Hanoi. And we did, what did we do? The last example was factorial. Okay, Wednesday, it is Wednesday. So Monday, we are doing the halting problem. And computability. And we may do so the question is that can you update OneNote? If you're using the same page again, you can have the pages, but we added to them this time. And I hope they're not just one page. So do me a favor, and if you're using your old notes, do some thing where you show that you've got the this is where the next day started, and then upload 2 files. So you can upload. There's a way in Gradescope to show where the next thing starts. Right? You pick where number 1 is. You pick where number 2 is. There's only a number 1 for these questions. So if you pick a number 1, when you pick your number 1 for the second day, actually show where that starts. If you would, please. Good question. And then we will do one last thing, which is this day, which is the Russell's. I can't spell today. And then we will do Gödel's incompleteness there. So this will figure out that stuff about computability. The whole reason for doing, the purpose for doing recursion is code, of course, because you'll be writing code. But the other reason to do recursion is to show that there are things you can't compute, and there are things you can't even prove. Are there any questions? Comments, issues, suggestions, thoughts? Okay. So that's it for me on Twitch. I'm going to log off Twitch, and I'm going to log on to the Discrete. I'm going to log on to Discord, and I will speak to you there if you have any questions you didn't want to say over me to repeat over Twitch. Okay? Thank you.